So thanks for joining us today. We're excited to be here in London and excited to be here with the Kubeflow community. Big thanks to them. I think they're doing a lot of great work and they're very supportive and collaborative. So really excited to be here. Another big thanks goes to our open source program office at our company. So I think they're supportive of us getting here and doing these talks. So really want to thank them for making it happen. Akshay and I work in a team that provides key data and ML technologies for Apple. And we're here today to present some work around speeding up your ML workloads using in-memory data caching. So let's dive in. At present, everyone knows in this room, GPUs are scarce and an expensive resource. And achieving efficiency in the cloud, in compute particularly, is an important topic. But it becomes paramount in the world of GPUs, right? We know there's fragmentation in passing data to GPUs, as the phases of data loading, deserialization, and transformation can cause GPUs to be idle, just waiting for these phases to complete so the data can actually get to the GPU. In this simplistic diagram, you can see the phases of the typical data pipeline feeding GPU in a single pod. These phases are I/O and CPU and memory bound, delaying the start of the GPU compute. These phases can be extra wasteful as they can be done repetitively for larger training workloads involving multiple GPU workers. So this presents an interesting opportunity for us to speed up ML workloads and to use these resources more efficiently. In order to achieve a better data flow, we introduce kind of sharding of the data set and efficiently reading those shards from a serialization optimized in-memory cache, reducing I/O and deserialization costs. The data can be fed into the GPUs more quickly and thus improving system throughput and GPU efficiency. So we'll discuss this in detail a little bit later. But first, I think it's important to point out that this technique presents a particularly interesting opportunity for larger scale training workloads requiring larger data sets. So I'll diverge a little bit and we'll kind of revisit topics on the big data space. So for years in high volume data environments, tools like Hadoop, Spark, HDFS, Parquet have been used for data processing and storage, right? Newer compatible technologies like Iceberg represent a big leap forward for efficiently storing and accessing large data in scalable storage environments. And columnar formats and table formats have matured to allow for very efficient access to large data while minimizing I/O ops from the storage solutions. As teams do more and more machine learning in big data environments, it is a natural extension of their work to use Iceberg tables to capture features and/or materialize data transformations to feed large data in ML training. Large data sets require training workloads to use more GPUs across more training workers. And Iceberg, Parquet, and the sister big data technologies like Arrow offer unique value to improve efficiency and speed of ML training. So now I'll hand it over to one of our brightest minds and an impeccable teammate, Akshay, to discuss how these key technologies can be combined on Kubernetes to solve this problem. Thanks, Akshay.
So for distributed training on Kubernetes, Kubeflow project aims to simplify, enhance user experience by modeling training using native Kubernetes APIs. And with the recently released Trainer V2 project, cluster operators can configure runtimes, which is essentially blueprints or templates that model training and fine-tuning using Kubernetes API, abstracting all the infra Kubernetes complexities away from data scientists and ML engineers. So engineers can leverage these runtimes and use SDK to create train jobs. It also has APIs to add initializers to streamline asset initialization that can be shared across nodes. This improves GPU utilization by offloading I/O tasks to CPUs. For example, here in this diagram, we have a dataset initializer, which is configured to run as a separate job to download datasets from Hugging Face and share it on trainer pods. And it has integrations with multiple ML frameworks and provides capabilities to scale model training from a single machine to large clusters using native Kubernetes API. And it integrates with advanced schedulers like Q to optimize on resource utilization. While Kubeflow offers flexibility and scalability to run distributed model training on Kubernetes, several challenges exist today when dealing with large tabular data, particularly loading dataset across multiple training pods. So large datasets can exceed memory of a single GPU worker which requires sophisticated solutions to shard the data. And with data parallelism, each worker would only need to access a subset of the data, and the challenge lies in how to efficiently select a subset from the entire data set. So in the previous example where we saw where the initializer shares the data set in a PVC, which is mounted on multiple worker pods, each worker would load the entire data set by default if using PyTorch GTP and select a subset from in-memory data set. Or in other cases with streaming, let's say, for example, using PyTorch iterable dataset, workers stream the data and select a subset without loading the entire dataset. But this will require workers to restream the data from source for every epoch, and which adds latency, IO latency, and GPU and CPU cycles. Hence, I think simplifying sharding of a dataset becomes a challenge to effectively utilize GPU resources and reduce the CPU usage and latency, especially with data loading. Also, maintaining consistent shuffling across epochs is essential to prevent overfitting and require solutions to, again, shuffle the data. So this also ties a similar problem on how to efficiently access unique subset of the data set for every epoch. So to address these challenges, in-memory caching can be an effective solution for GPU workers to readily access data in an optimal way, improving efficiency and reducing CPU bottlenecks. Specifically for tabular datasets, this would reduce CPU cycles spent to convert data from a storage-optimized Parquet format to a format which is consumed by GPU workers. And with repetitive access pattern during training, cache reduces the need to fetch the data from slower disk storage or object stores, minimizing IO latency, which is typically time-consuming and latency-prone. Also with distributed caching, it also allows data to be partitioned and stored across multiple nodes, and this enables parallel access to these shards from multiple workers, improving latency and throughput. And by loading or streaming only a portion of our data set into memory, each worker requires less memory, reducing the overall memory footprint. Also, by providing direct access to the sharded data with caching, it can easily allow workers to access specific shards across epochs. Also, when multiple training jobs access the same data set, caching solution can greatly improve resource usage, reducing the need to re-download and reprocess the entire data set from storage. Hence, the proposed solution, this slide actually talks about the overall high-level architecture. And the proposed solution consists of loading and caching the data in an Iceberg table, for example, in a Parquet format to a memory-efficient Arrow format. So Arrow is an in-memory columnar format supporting zero-copy reads when sharing data between multiple processor systems. It's specifically advantageous to use with tabular data, which is already stored in columnar format on disk storage and object stores. It also supports streaming, allowing clients to process batches of data, overlapping with the time spent to deserialize the next batch. And the architecture uses data fusion to actually shard, Apache Data Fusion to actually shard the dataset and allowing clients to actually query shard of Arrow data. So Data Fusion is an embedded query engine that uses Arrow format and provides fast in-memory processing capabilities on columnar data. It is extensible by design and has several integrations with table and file formats like Parquet. And finally, to stream the dataset from cache to GPU workers, the solution leverage Apache Arrow Flight framework. Flight uses gRPC API to actually send and receive Arrow arrays. It optimizes gRPC API to directly access in-memory buffer of Arrow data to convert it to an IPC format with no serialization overhead. The Flight framework also allows clients to access the data directly from data nodes without streaming from coordinator, which improves the resource utilization, particularly when dealing with large data sets. Here we're providing high-level overview of the functioning of the cache. Here, this slide specifically describes the bootstrap of the cache with data and head nodes. So during the bootstrap, head nodes can scan the Iceberg table to fetch the metadata of relevant data files in the table. It then groups the data files equally based on the number of rows into logical shards. It then distributes the shards to data nodes in a round-robin fashion. And then the head node constructs an index table, which actually stores the metadata about individual shards. So this table contains information like the shard location and the range of the rows in that shard. And the other hand, the data node loads the data from these data files into Arrow format in an in-memory table and adds an indexing column for every batch as it loads to the table. So head and worker nodes today are implemented using Rust-based data fusion for transforming the Parquet files to in-memory Arrow tables and use the data fusion actually for its memory efficient query execution to query these tables. So once the cache is ready, so this slide talks about how GPU workers can access and stream dataset from cache. So let's say in this case, like head node is responsible to auto shard the dataset logically based on the number of GPU workers in a training job. And workers access the shard using a shard index that is passed to head node using the flight protocol. So in this example shown in the slide, so rank 2 of a train job accesses a head node first to know about the location of the shard with index 1. Head node responds back with the endpoints to access, which allows the clients to directly access the data nodes to fetch the data. So in this case, shard lives in both data node 1 and data node 2. And workers then connect to data nodes to access the shard using a range query on in-memory table on a data node. So this architecture implementation with data fusion is beneficial as for specific reasons, like the data is stored in Arrow format, and using data fusion to select a range of rows from a table is very efficient and fast, as data is represented as continuous block in a memory. And since the head node creates logical shards, it doesn't require to reshuffle the data across nodes. Hence, multiple jobs with different topology can access the same cache instance, which would allow for reusing of the dataset let's say, for example, a Kubernetes cluster. And to shuffle shards across epochs, clients can dynamically compute shard index, which can be different for every epoch. So the slide describes key concepts with Flight framework and Flight client that can be used to stream the data using Flight API. It actually talks about creating a Flight descriptor, which describes about the identifier to access the data shard, and the client passes this info to the head node with the get flight info call to fetch the flights. And each flight consists of an endpoint to access and a ticket that's required to pass to the data node to access that specific shard. And if the shard that's being accessed lives in multiple data nodes, like we saw in the previous example, the flight info would have multiple flights in the response. Using this flight info, clients can stream Arrow record batches from data nodes. And in the demo, we'll also see how we can use this flight client with PyTorch data loader to actually access the data from cache during a training run. And to leverage cache with training on Kubernetes, users can easily integrate with Kubeflow. Users can extend any of the existing runtimes, which are the blueprints which we talked about earlier, to add cache initializer as a dataset initializer. And once the cache is up and running, workers can be scheduled to access the data from cache in parallel. So currently, the lifecycle of the cache itself is tied to the train job by adding the owner reference, which would launch the cache specific to the job and destroy it on the completion of the job. And the cluster is deployed using leader worker set API on Kubernetes. The leader worker set is used to this advanced specifically, like deploys cluster as single unit, and that can be used to easily scale it with multiple replicas for fault tolerance and HA. It provides a failure handling with all or nothing restart across the nodes, avoiding partial failures in this case as data is in memory. It also provides support for dual templates, which advantages here because the data nodes might require more resources compared to the head nodes. And also we're excited about the future roadmap of this project because it also inline to support gang scheduling, enabling all or nothing scheduling of nodes with the launch of train job. And this slide specifically talks about how easy it is to configure and create train job with cache. As a cluster operators can actually update existing runtimes with the template spec to add custom initializer job, and ML users on the right side can easily create a train job using the passing the dataset initializer config, or the data source config with using the SDK. The API itself is extensible that the operators can configure cache initializer to launch the cluster on CPU node groups, specifically with memory optimized instances for warming up the cache, and leveraging using CPU groups because it's a CPU intensive task, and leveraging GPU nodes to schedule training pods. Using this example, we also want to demonstrate how Kubeflow trainer can be easily extended to support various use cases. Now we'll see in the demo how easy it is to integrate with PyTorch to fine-tune an LLM. So here I have a notebook where it's actually using BERT model to fine-tune using an LPreview dataset using Kubeflow train job. And the LPreview dataset is currently in an Iceberg table. First, user can would need to install the SDK. And using the SDK, users can access the Kubeflow train runtimes. So here with SDK, we can list the runtimes. In this cluster, let's say I have 3 runtimes. I'm specifically interested in the runtime distributed cache. So this has all the config which we talked about earlier, where we added the cache initializer as a first step during the run of the train job. And the next step we'll specifically use to create a training function which would actually access data in the cache. In order to do that, we are interested in creating a cache dataset API, which is an iterable dataset from PyTorch, taking in the batch size. And in the iterator, in the iterator, we actually calculate the shard index dynamically for that specific dataset and use the flight client, which we described earlier. Here I'm using Apache Arrow Flight client, creating a flight descriptor and passing that flight client descriptor with the shard information, shard index specifically, and connecting to the head node to get the list of endpoints, and connect to this data nodes using the endpoints, passing in the tickets, which has the range of rows to actually stream. And then I'm converting the record batch, the arrow batch, into chunks where each chunk is of batch size. And in the chunk, we'll specifically use a function to convert the arrow record batch data to a tensor. For that, let's say, for this specific example, I'm using LPreview dataset. So I'm overriding my function to actually convert the record batch to a tensor by converting using the Arrow APIs to actually convert to PyTorch data structures with no copy, which is the benefit of Arrow data. And using tokenizer from Hugging Face to actually encode and converting it to a tensors and passing the tensors back. This actually is using a PyTorch data loader to train the function, to load the dataset from the cache, and I'm running a training loop here. And once we define the training function, the next step is to use the SDK to create a custom trainer, pass in my train function and the configuration required for my training job, and required packages to install in this case. And in this case specifically, I'm accessing a specific Iceberg table. So I'm passing in a custom dataset config, which is Arrow dataset config. I'm passing in an initializer with the custom config here. Here I'm just accessing static table. So hence I'm using my metadata JSON file. And also once I configure the initializer, I'm also passing the runtime which I'm interested in, where I configure the cache. So I'm creating a training, I'm triggering a train function. You can use the SDK to actually list the train jobs. Now the train job is in created state. I can also see my the initializer is actually triggered by the runtime, which uses the runtime initializer, and it triggered a cache. This is a leader worker set cache instance, which is triggered directly from the train job. and it would wait for the cluster to be cache cluster to be ready, and once it's ready, it would the train job would trigger the workers in parallel. These workers are configured. These workers would access the cluster to access the data without any deserialization cost. Users can also use SDK to actually check the status of the job, and also stream the logs directly from using SDK. Here in this case, I'm actually streaming the logs from the trainer node 0, and where it's accessing the batch, record batch, and converting it to census. So this just demonstrates how easy it is to plug the cache into the lifecycle of train job. Going back to the slides here. So reiterating the benefits with cache. So users can easily access the tabular data from cache without worrying about sharding of the dataset across GPU worker nodes. Users can see improved GPU utilization as workers consume data via zero-copy arrow streams, eliminating the need to deserialize the data. And it supports direct conversions to pandas or NumPy. So dataset initialization pods can be scheduled on GPU nodes, freeing CPU nodes, freeing the GPU nodes from compute-intensive workloads. And users can also launch training workers with reduced memory and disk size, as clients can stream a batch of data from cache. Users can also easily shuffle globally across partitions while maintaining per batch in-memory shuffling as well. And multiple users running training jobs in the cluster can access same dataset cache irrespective of the number of workers. And the users can also leverage Kubeflow, a trainer API, to provision and access cache without any overhead, simplifying the creation of jobs using SDK and runtimes. So, regarding the future work, we have proposed an enhanced KEP with Kubeflow community, which we shared with the community, and we are soliciting feedback from the community. And we're also working on benchmarks. So currently, as a next step, we also want to support accessing dataset via catalog. Right now, as an example, I just showed how easy it is to access via a static table, but we want to support catalogs. And also, we want to support calculating the cluster size based on dataset size without requiring users to configure the size of the cluster manually using the train job SDK. And right now, the lifecycle of the cluster itself is tied to the lifecycle of the train jobs. So we want to support reusing of the cache from multiple jobs as well. And also we want to support custom Iceberg types and tensor types. And we want to try to see to support trainer V1, Kubeflow trainer V1 as well. This has the link, QR code has the link to the proposal which we shared with the community. And yeah, let us know if you have any questions. Thanks.
Maybe go back to QR for a second.
I think we have 1 minute for the question. Any questions from the audience?
Andre?
Yeah, go ahead. Can you take the mic here and feel free to ask questions? Let me bring you the mic.
Well, thank you very much. I have actually a very simple question. I don't think we have been using these more advanced ways of training. We've been using Kubeflow for 45 years. Not 45, 4.5 years, I meant to say. And we just train on the pipelines, and we have a lot of issues with that. Sometimes the pipeline fails. But one of the common issues we have is that we are lacking these gigantic data sets. And my question is, like, this dataset initializer, is that something you created from scratch? Is that something that's part of the cluster training runtime? Because I'm not familiar with this. Yes. I haven't used it. Yes. Would be nice to learn something. And
yeah, I can answer the question. So I'll repeat the question. So basically, the question is about the dataset initializer, as I understand.
Yes.
So
yes.
yeah. So with the new runtime APIs, Trainer V2, Kubeflow Trainer V2, it has initializers which can be configured as a separate job. So you can configure your runtimes with the dataset initializer, which can be a separate Kubeflow job. You can have your template spec which is like a job spec. So you can use that spec, and you can have your own initializers like Docker image and also config.
But you coded this from scratch. Let's say you created the job, you created this job, and then you just added. You can add whatever you want.
Yeah, you need to just parse as part of the runtime.
Okay.
And the trainer APS will create the job as part of the initialization of train job.
And do you so follow up? Do you have this publicly shared? Like
Yes, it is.
Okay.
I think trainer V2 was released I think a while back. Yeah, you can check the documentation.
I mean the dataset initializer, is that something you could share with the community, or
so
is that
specifically dataset initializer, the Arrow data initializer is something which we worked on, so we'll be sharing it with the community.
Yes, please. Thank you. It's very useful. Thank you so much.
Yeah, it's a great question. Yeah, we're working on to make it extensible, support for inference, for pipelines, not for training. So definitely, you can leverage from this. You can benefit from cache from many stages of our lifecycle. All right. Thanks, speakers. Great talk. Super excited about it.